Hi everyone, shalom lekulam. Today I came especially for this meetup from Poland. That's true, but that's not all the truth regarding my visiting Israel. I'm actually pretty often here. That's one of my favorite cities in the world. I'm in Tel Aviv, so I'm very sorry. I know that I'm in Ramat Gan, but that's why I showed this direction. But Ramat Gan, technically Ramat Gan is another city, but I think it's a great city as well. Today we're here to talk about leveraging word embeddings, so a method from natural language processing for the purpose of building an efficient recommender system. And what do I mean by efficient? I will tell you in a second. But in the beginning, I want to give you a brief overview of what we will be talking about. So we'll start with an intro, then we'll do a short refresher on embeddings, very short, but if you will have any questions, feel free to ask them. Then we'll talk about doing recommendations with embeddings, so using embeddings. And at the end, we'll talk specifically what can you do to make your embeddings well suited for recommendation settings. Right? Because this method comes from NLP, and natural languages, they have certain qualities that might be different than the qualities of products, or product descriptions. So 5 sentences about myself. My name is Aleksander Molak. I work as an innovation lead and a researcher, machine learning researcher at Lingaro, which is a global company doing data consulting, let's say. I'm an expert in NLP. I'm very interested in probabilistic modeling and causality. I'm the author of Sunday AI Papers, which is a LinkedIn-based microblog where every week I review papers from the last week. So let's call a bleeding edge stuff. I'm also interested in complex systems psychology and neuroscience, and that's a part of my academic background. And things that I enjoy privately is traveling with my wife, which I'm not doing this time. I'm traveling alone. It's also running, vegan food, and languages. Yeah, so let's go to the intro. And I want to start with telling you a little bit about what I mean by efficient. So we talked about efficient recommender systems, not recommender systems in general. And I think this is important in the context of this presentation. So first of all, I want to talk about a system that is relatively easy to develop. Second of all, it's relatively easy to maintain. And third of all, it offers fast inference time. So we want something that, even for a large amount of data, is able to provide you with predictions, like production-grade predictions. So now let's do a quick refresher on word embeddings. That's one of the definitions of word embeddings that I found somewhere, maybe on Wikipedia. I don't think it's the best one, but it has some interesting parts. So it says, an embedding is a relatively low-dimensional space into which you can translate high-dimensional vectors. So in the context of natural language, those high-dimensional vectors are actually implicit. So we can think about any word that comes to your mind, like maybe cat, and you can say that cat can be described as a virtually infinitely dimensional vector.
This is any mathematical embedding. So I think word embedding is a special case.
Yeah.
Any embedding would fit here.
Yeah. Yeah, it would, yeah. But we are talking about NLP, so that's why I'm talking about those cats. Yeah, or is there something deeper in what you said that I didn't catch?
Just general thing.
Yeah, okay. So for instance, cat could be described by an embedding where we have one dimension that says, is it an animal? And that will be a binary 1 or 0. Then maybe has it fur? That will be a probability because there are cats without fur and there are cats with fur, and so on and so on. And we can think about those dimensions on and on. And when we are training training word embeddings, we actually have those high-dimensional vectors that are only implicit, and we are trying to map them through the neighboring words. So we have words and their neighbors, and we say that the context says something important about the word itself and its meaning. And the most important thing in the context of embeddings in general, but also word embeddings, is a fact that it gives us a representation that has some useful properties. So one of those useful properties is that things that have similar meaning or are semantically similar will be close to each other, like cat and dog, and things that are not are further away, like car and Andromeda, for instance. So the way we build those embeddings, the idea comes from, it's not a new idea. This is a very famous quotation from John Rupert Firth from the 50s, where he said, "You shall know a word by the company it keeps." So this is a quotation that you can find very often in the context of word embeddings. But actually, this idea is even older. And this is another sentence, this time from Ludwig Wittgenstein, who was Austrian Jewish philosopher. "For a large class of cases, though not for all, in which we employ the word meaning, it can be defined thus. The meaning of a word is its use in the language. And use is always embedded in some context. This can be context of other words, but it might also be situational. And this is what Wittgenstein was talking about. Another interesting property of embeddings, word embeddings, is that we can do a kind of embedding arithmetic using those, right? So we can take some vectors, and I'm pretty sure that everybody who knows something about NLP have seen this illustration before. So we can take king, a vector for king, subtract man, add woman, and we are expecting that we'll get something very close to the vector for queen. So now, if we can use this arithmetic for words, could we also use this for products, for instance? So I think we could use it for products, and there are a couple of useful things here. So first of all, we might embed products that are similar, close to each other in this embedding space. That's useful per se, I guess, because as you can think of it, it's easy to search the points that are close to each other. A product? Oh, okay, yeah, that's a very good question. So a product is represented either by some code, or maybe just its name, or maybe its description. So any of those will work.
Like a supermarket.
So a product is like dry gin something, 300 milliliters. Apples, 1 kilogram. It might also be just a code for apples, which would be 20458, right? So any of those would do, and they will have slightly different properties. We'll talk about this a little bit in a bit more detail later. So one interesting property is that we have those points that similar products should be somewhere close in this space. But another one is that we might be interested in recommending a product based not just on one product, but on a whole basket of products. And now, thanks to this arithmetic that we have here, we can build an abstract representation of a basket of products, and it will be somewhere in this space, k-dimensional space. Okay, so how to do it? First of all, we have a couple of different scenarios that we can find useful in our use case. So we can model inter-product relations, which means that we have a basket of products, and we want to embed them in the embedding space, and then be able to use all of those features that we talked about before. Another use case is that we might want to leverage meta relations between those products. So for instance, you can imagine a supermarket, and in the supermarkets you will have aisles, where you have maybe one is with vegetables and another one is with vegan products. And then you might be interested in not only modeling the relationship between the products within someone's basket, but also a relationship between products given that they come from a given aisle. So this is something we can also do. And finally, we might be interested in encoding morphological information about products. So leveraging the information that is encoded in their names or descriptions. And this comes back somehow to your question about what is a product. Because if we represent a product as a code, then this last thing won't work for us, right? But otherwise, when we have names and those names are meaningful, so maybe apples 200 grams and apples 1 kilogram, there are similar products. And then we can encode this morphological information. This first use case, we can actually model this using a plain word-to-vec model. Who has heard about word-to-vec model? Okay, so like almost everyone. The second one, if we want to leverage the second one, so if we want to add meta relations, we might be interested in using another model, which is called Metaprop tovec. So who has heard about this model? It's like 2 people, 3 people. Okay, so I'll tell you a little bit about this. So in word2vec, as you probably know, we are either trying to predict the context given a word, or we are trying to predict a word given the context. So that will be a skip-graph model or SIBO, or continuous bag of words model. In Metaprop tovec, we are not only taking the product embedding, so the product name, let's say, but we are also taking the context, and we are modeling jointly both. So we can think of it as trying to predict the context, and the product based on another product and its context. So for instance, we can go back to this example with ale. So we say maybe vegetables, and then carrot 1 kilogram. And then another product in our basket would be beverages and Coke Zero, for instance, right? So now we are not looking at single items in a vector of our products and context, but we're looking at tuples. Okay, so we are taking into account tuples. It looks maybe a little bit more complex than word2vec, but in practice, it's not really more complex than the model. So we just need those tuples, and we need to make sure that those tuples are always together. So when we shuffle our data, for instance, we make sure that our context and product names are one next to each other. To encode morphological information, we can use another, let's say, another type of word2vec model, actually, which is called FastText. Who has heard about FastText? So it's like about 50%. So the main idea behind FastText, it's very similar to word2vec. The main difference is that before we are embedding the tokens in the space, we are splitting them into subwords. And those subwords, how we split those words into subwords, is usually driven by the frequency of those subwords. So maybe DE, like that, would be one subword, and I don't know, SE and SA would be another subword. Does it make sense? Yeah? Okay, so let's see how to implement it. That will be very high level, but just to give you a glimpse. So one remark here is that all the code that is here is using Jensen API version 3.8, which is one before the current one, which is 4.0, I guess, 4.01. This is very straightforward. So we just import the class word2vec from Jensen, and then we just pass the data, our parameters, and some callbacks if you want to use them. And our data should be in the form of a list of lists or an array of arrays of strings. So now I want to talk about hyperparameters a little bit. This goes back to what we said in the beginning, that there are some attributes of natural language that are not necessarily attributes of, let's say, product descriptions, and so on. Who of you has heard about Zipf's law? Zipf's law. Yeah, Zipf's law, sorry, yeah. Okay, so it's like, yeah. Thank you. So I will talk about this briefly. But let's start with the architecture. So we said in the beginning, most of you are familiar with word2vec model, and we said that there are these two different architectures called CBOW, continuous bag of words, and skipgram. And for recommender systems, from my experience, skipgram usually works better. They are either very, very similar, or skipgram is better. So from my experience, I would say that if you want to use this for recommender systems, skipgram should be your way to go, or could be your way to go. Now, another, or let's say the first of the hyperparameters when we decide on the architecture is called subsampling. So this is a very important parameter, and if you know the original word2vec paper from Mikolov et al, you might remember that they also talk about this. So subsampling reduces probability of using the most frequent or the least frequent, depending on the parameters here, words in the training. This formula comes from Google implementation of word2vec, so it's slightly different from the one in the paper, but they are very similar. And just to see what it does, maybe one more thing. I will go back here. So in the word2vec paper, the value of k is just some constant, right? The value of k is 0.001. We'll see this in the graph in a second. So 0.001 is the yellow line. So here you can see the frequency, and yeah, and you see that the words that has very low frequency have very high probability of being taken into account when we train the model. While words with like very high frequency, their probability is much better, much lower. I'm sorry. Yeah. So why is that? Anybody has an idea why that could be? Mm-hmm. Everyone buys eggs. Yeah, that's a good one. But when we go back to the natural language setting, why would we like to train on the words that are less frequent in the language rather than on the ones that are very, very frequent?
Like strong positions, and positions, like all this syntactic stuff that's not very meaningful.
Yes, exactly. That's a very good answer. So the first answer was that everybody buys eggs. This is an important realization when it comes to recommender systems, but when it comes to natural language processing, the answer was that all the syntactic stuff, things like things like a, they are not really meaningful. So we are not really interested in modeling them. But for the recommender system, actually, of course, it depends on your setting, but for many of those, we actually want to recommend products that are popular. Yeah? Of course, that depends on your setting to some extent, but in many settings, if we sell a lot of something, we want to sell even more of this. So that's why for recommender system setting, we would rather go with a line like this, which is almost flat, as you can see. So that would be something close to 0. Another very important parameter is negative, so-called negative sampling. So in word2vec, we are not taking all the samples as our negative samples, because that would be very, very inefficient. So we are trying to sample some negative words to make the training feasible and much more efficient. There's another formula here, but I will show you the plot. So that's the frequency of words versus their probability of being chosen as a negative example. And as you can see, the yellow line again shows the values for, shows the distribution for the value for natural language that was proposed by Mikolov. And it goes like, it's a little bit lower here and a little bit higher here. But for recommended system, again, we have slightly different situation. So we want to take something that is very infrequent as our negative examples pretty often. And this is something that worked for us in practice many, many times in different settings like retail, like HR, and so on. And for actually all the projects that I use this method for, the values between -0.5, -0.45, and -0.55 are optimal. While for natural language processing, we usually use something around 0.75. For English, it seems that it's an optimal value. If you want to go into more details on this, there's a very nice paper on this called Word2vec Applied to Recommendation, Hyperparameters Matter, from guys from Diesel. I don't even know if this service still exists. And this is an example of a set of hyperparameters that I actually used in one of our projects. So the embedding dimension is 300, window size is 9 here, and 9 works well if you are modeling with the context, so using Metaprop tovag. And then we had 2 context levels, right? So there was a hierarchical relationship of 2 levels, and then product, and then a product. But if you have like a flat, non-hierarchical situation where you only have products, then a window size that is a 95% of maximum length of your, let's say, basket works pretty well. And then you see that the negative exponent is -0.5, so something we discussed before, and sample, which is subsampling, is 0 here. And that was these values were actually tuned using some Bayesian methods, so they come from tuning on a particular problem. So now, if we have a recommended system over like a very, very large search space, one of the problems is that it might be hard to find those nearest neighbors. So for this, there's a method called hierarchical navigable small worlds, which is a non-metric, which maps this metric embedding space into a non-metric space and builds a kind of a hierarchical structure that is very, very easily searchable. And this gives you a very high recall with like a very, very fast inference time. So we use this for a data set where we have over 4 million entities. And for those 4 million entities, we're able to get predictions in less than 100 milliseconds. Yeah?
Why don't you use maximum inner product in your search?
I think it's, well, I think that will be slower.
How does it work?
So this maps a metric space of embeddings, which is like, in this case, it was 300 dimensional. It maps it into a non-metric space based on a graph. It's not actually one graph, it's a hierarchical layered graph structure. Yeah. So I know this is a kind of high-level answer, but it will be hard for me to describe it in a very detailed way. But if you're interested in this, I can link you a couple of papers on this, which are very interesting.
But you mean that hierarchy is what makes it efficient to relate?
Yes, it's one of the aspects, yeah. And another one is that
It's more robust.
it's more robust.
Inner product
Yeah.
tend to be not robust.
Okay. Yeah. So the remark here was that the inner product tends to be not very robust. This is very robust. Yeah. So you can get like a very high recall. I was actually comparing this method to the exact search, and in most cases that was like 100% coverage. So they were identical in most cases. Yeah. But there's like a very good benchmark somewhere on GitHub where people just did a shootout between many methods, including this one. And this one is really, really superior. When I read this for the first time, I was like, wow, I was so stunned, you know? So if you're interested in this, let's link on LinkedIn, and I'm very happy to send you some materials on this. And another interesting thing is multi-entity type scenarios. So this might be, for instance, you might be interested in embedding different entity types in one space. Maybe it would be like in HR space, skills, job titles, and employers. And now when you do this, it has some advantages, some disadvantages, but if those advantages are important to you, then it might be a good idea. But one problem that appears then is that if you want to search for an employer given a set of skills, for instance, and your data is slightly noisy, which means that you will have some actual skills as employers, then before you, in the space, you reach to employers, you will go through all the skills, including those that are not real skills, but those noisy employers, actually. And this makes it very, very hard to actually make it useful. And to deal with this, one simple and good idea is to do space partitioning, which means that after the training in one joint space, you just partition this space into, in this example, 3 different parts. And then if you want, for instance, get a job title given a set of skills, you just embed the skills, build a representation for all of them, and then search the space of job titles using this representation. There are a couple of insights that I would like to share with you. So when training, shuffling either helps or is neutral. In many cases, for me, it helped. Although I was convinced that the data is already shuffled when I got it. I thought it has like completely random ordering. But shuffling helped many times for me. But sometimes it's neutral, so it doesn't help. One thing to remember is that if you use Metaprop tovec, then you need to remember that you need to keep the ordering of your tuples, right? You need to shuffle tuples, not each of the entities in your list. Another one, something that we talked about before, skipgram usually performs better than continuous bank of words in this context. Euclidean distance outperforms angular distance in some scenarios. This is something that I was surprised myself by at some point. Because if you think about those metrics, like especially distance metrics in higher dimensional spaces, they tend to lose their meaning, right? If the space is very, very highly dimensional, Euclidean distance will tend to go to 0 and just lose its meaning. But in some scenarios, it performed much better than angular distance, which was cosine similarity in this case, and it was like more than twice better. So it was really a significant improvement.
Cosine similarity assumes all the vectors come out from the same location, the same spot. Mm-hmm. And Euclidean distance doesn't do that.
So the remark is that cosine similarity assumes that all the vectors come from the same spot, the same origin, right? Is that what you mean? Yeah, the same origin, and Euclidean distance does not assume this. And I think that it's a very good hypothesis. So in a sense, when we measure cosine similarity, we might have a couple of vectors that are one behind another from our perspective, and then another set of vectors that are one, or points that are one behind another. And now cosine similarity for all those points will be virtually the same. While for Euclidean distance, it won't be, right? So I don't know if that's exactly what you thought. Yeah.
Projective plane.
Sorry?
There's, if you project that use the projected geometry of the Euclidean space, you get the angular matrix.
Yeah, so, yeah, projective space, that was the remark on. Yes? Yes?
It's very nice to have the recommendations. I just want to ask you, in this world of hyperparameter tuning and model tuning, do you think that we don't need this like recommendations anymore, and we can just base our data and let it run for the night, testing all those possibilities and just output the perfect model? Is it like possible with SageMaker or other pipelines?
So the question is it possible to run this type of model using SageMaker or another cloud-based service, right?
And let it find those recommendations itself.
And if this service would be able to find these recommendations itself.
Do you think that we are at this point like?
One challenge that we have here with recommendation systems, I think, is it's not always very straightforward to find a good metric, right, to optimize. So in some cases, we were using a very simple statistical frequencies or like frequency table as our comparison metric, right? So that was, let's say that was our test set, yeah? We're using this as our test set. Now, if you have a good metric though, I think that's perfectly possible because this is actually just a regular hyperparameter tuning scenario, right? So if you have a good metric and a good test set, then you can just put it in some auto ML stuff or like automated hyperparameter tuning stuff, and it should give you all those parameters. Yeah. Does it answer your question?
Yes, but those are like fine-grained parameters, and we are thinking about even in the model level, like we're just thinking about like giving it the data with the labels and going home and coming in the morning and just.
Mm-hmm. So one thing that is different here from the scenario that you described, because you said something, and I will repeat this for the recording. Is it possible that we just give the data and the labels, put it to the service, and come back in the morning and have the model trained? Is that correct? Is my understanding correct of your question?
Yeah.
Yeah, okay. So that would be possible, of course, but here we don't have labels, right? Most of the time. We might have some baskets, like other baskets of products that people bought, maybe, but there are no labels. So this is like an unsupervised learning scenario. What we are trying to optimize here is a type of essentially a contrastive loss, right? So we are trying to infer labels, quote unquote labels, from the context, and that's all. And that's why I said before that if you have a good test set or validation set and a good metric to compare your test set or validation set with the outputs from the model, then you can do it with automated hyperparameter tuning. Because then it becomes just an optimization problem, right? Maybe a little bit more complex than some other problems, maybe a little bit less complex than another set of problems, but it's just an optimization problem. But we don't have explicit labels here, I would say. Does it answer the question? Yeah? Okay.
I have two questions. One, how will you change these things if you have a multilingual data set? And did you consider using some Barrett or another sentence encoder instead of tovec to capture the context and still use it in the
So the first question is about language. So I will speak like this. So the first question is about how could we leverage this in a multilingual setting, right? And the second one is, could we use a type of embeddings like maybe BERT or something like dynamic embeddings? So when it comes to multilingual setting, you can try a couple of things. So you can try translations. That's one thing. If you have a good basis for translations, that would not always be the case. You can try also, that's something that we're working on in one of the projects. You can just train different models for different markets if your languages are related to markets, because then those markets might have their own ways of being, right? So then that's another thing. If you're in a scenario where you can use pre-trained embeddings, so maybe you don't have just product names, but maybe descriptions that are more comprehensive, then you can use some pre-trained embeddings, maybe FastText. FastText works really well for automatic language detection if you don't want to use APIs like Google Translate and so on. So I think those representations are kind of good to give you a reliable multilingual space. Does it answer your first question? Yeah, okay. The second question was about dynamic embeddings, paraphrasing, if you will. Certainly you can use dynamic embeddings, but in the context of this talk, they would not necessarily meet the criteria that I gave in the beginning for being efficient, right? So the inference time for BERT is, it's doable to have it in production and low latency, but it's much more challenging. This system, you can actually run it serverless. So you can put it in Azure Functions maybe, or GCP or Cloud, I don't remember the name of this service. Yeah, but there's one, GCP, or AWS Lambda. So this is this kind of efficiency, right? So for BERT, that would not work. But of course, if you have more resources, you might use BERT, but I would see BERT as meaningful probably in the more comprehensive description scenario, where you don't have just product names. If you just have product names or product codes, I don't know. I don't have a good use case in my mind, just like this. Maybe there is one, but I don't have one that would justify the overhead for development and inference time and maintenance as well. Does it answer your second question? Yeah, thank you. Euclidean distance, and the fourth point here was about space partitioning. So this is something that we also talked about briefly. This might make your system faster when it comes to inference, and just make it much more robust if your data is somehow noisy. So space partitioning might help you address these two questions. So pros and cons. First, I think it's easy to maintain, very easy to maintain. You can schedule automatic retrainings. You can train it continuously as well. So you can just, train when the new data comes, but not from scratch. You can model complex interactions. So this is a big advantage over, let's say, some simpler methods. Then it supports continuous training. That's something I already said. It's relatively fast to train. Relatively, because if your data set is huge, it might train even on a large machine for a couple of days. It has ultra-fast retrieval times using H and SW, and it can be easily served in a serverless fashion, depending on the number of tokens. Because if your vocabulary is really huge, it has hundreds of millions of tokens, it might be challenging to go serverless. But in most cases that I worked with, it worked pretty smooth.
So you just, in the implementation, currently we're using SageMaker with endpoints. So you're suggesting using the GenSim with a volume with AWS Lambda.
Yeah, Lambda would be one solution. If AWS is your cloud to go cloud, then Lambda should do the job here.
So it's just a Jensen framework running with the volume, with the model retrained volume.
Sorry, I didn't understand the last volume.
Just like a function that's running Jensen function.
Yeah. It's running. You need some code around this usually, because you need to parse your query and stuff around this. But essentially, it's a Jensen model inside of some wrapper code, some boilerplate code. Yeah. Does this answer your question?
Yes. Maybe I just thinking maybe we need to like run like an ensemble model with our predictions with this.
Mm-hmm. Great. I mean, if you will find this useful, I'll be more than happy. And that's the best thing that you can get out of a talk like this. If somebody comes here and then goes and tries this in their use case and it helps them somehow. So yeah, and there are a couple of cons as well. So the main one, I would say, it's not suitable for cold start scenarios, which means that if you don't have a lot of data in the beginning, it will be very hard for you to build meaningful embeddings, right? So you need to have data first, and then you can train the system. The second thing that I found very challenging in some projects that I worked in was that if the data is noisy, the predictions might be noisy as well. So there is virtually no mechanism in where tovec that can help you out of the box, can help you with denoising your data. And there might be many different types of noises. The one that is the most annoying in this case is when you have entities, when you have a multi-entity scenario and you have mess in your entities. So maybe you have entity A, type of entity A, and type of entities A, B, and C, and then you have some entities A in the set of your C entities. So that's a very difficult, might be very difficult scenario. And that's the last thing I wanted to share with you. So thank you so much. If you have any more questions, this is a very good moment for them. How do I explain that Euclidean loss is better, and have I tried other types of losses? So when we are talking about Euclidean distance here, it was not in the context of loss function.
Sorry, distance.
Yeah, it was about distance. So I think, sorry, I forgot your name. Ariel. Okay, so I think this is what Ariel said before, that if we have some points that are, one behind another from some perspective, and then we have another set of points that are one behind another from the same perspective, looking from the source, then cosine similarity might not work very well, because all the similarity between all of those points in those two groups will be the same. While a Euclidean distance should capture the differences between them. And I'm not sure if this answers your question, because
It goes vice versa. So
vice versa, okay.
You have like the same distance, different angles, and the Euclidean would be mistakenly.
Okay. How the fact that if you have points in a sphere that have the same distance from the center of the sphere is related to embeddings, how that work, right?
So that's like an artifact.
Yeah, that's like an artifact. It is an artifact, that's true. Though I think we need to remember that we are not in three-dimensional space, we are in much higher dimensional space. And if we are lucky enough, so the points are spaced in a way that can be still meaningfully measured by Euclidean distance, it's very unlikely that they will have exactly the same distance from one point in these 300 dimensions. That's at least my observation when I was looking at the systems, right? So from the projections, like lower dimensional projections of those embeddings that I worked on, I suppose that sometimes, in some cases, they actually form a spherical, some spherical shapes. Sometimes these are bubbles. Like we talked about this multi-entity scenario where we have maybe skills, job titles, employers. They tend to form three separate bubbles in the 300-dimensional space. But the spacing between points within those bubbles it's really the case that those distances are very, very similar between any 3 points, let's say. Of course, this is something that's another type of noise that we have in this type of systems, which is inherently connected to the nature of this system and what you actually mentioned. Now, this goes back to a question that I would say is somehow philosophical. So what does it mean to be similar, right? Is it only co-occurrence? Is it semantic? Is it like a semantic similarity? Is it maybe something else? What do we mean by this as humans, right? Now, these points might be close to each other for many reasons. One of them is that they are directly neighbors in many, many records, right? But as we said in those pros here, we can also model very complex interactions. So they might be very close because of some spurious correlation that goes through many, many different products, right? Because with every iteration when you train Web2Vec, you modify the whole space in a sense, right? So this is a challenge, and I don't have a simple answer to this question. I could say that for whatever reason, I mean, I cannot find a definite theoretical justification for this, but for whatever reason, if your data is not very noisy, this system just tends to work very well. So the outputs are usually very meaningful. If your data is noisy, it becomes problematic. And I don't know if this answers your question. That was a very long answer, but I don't have a definite one and try to give a little bit broader context. Is it satisfying?
Yes, thank you.
Yeah, okay, thank you so much. Okay, any more questions? Maybe one or two, because I feel like we already used a lot of time, right? Okay, no questions. Thank you so much.